We got 15 minutes. Yes, I can get through most of it. All right, so your homework tonight, you don't really have any, but if you want to get started, you can. On Monday, 5 and 6 will be due. So that's up to you. All right? Danny, you'll come and see me for a book? All right. I think I have a total of maybe 3, so if anyone else is like dying and I haven't given you a book yet, please come and see me. Yes, at lunch. All right. Interior point. Continuity at an interior point, the definition is the limit as x goes to c of f of x is equal to f of c. But I'm going to back up a little and say, well, if the limit was to exist, what had to have happened first with the 2 arrows? The limit as x goes to c from the left has to equal the limit as x goes to c from the right. So I'm reviewing the definition of a limit. That's the blue and this piece of the red. That has to be true, but then on top of it, we have to be equal to f of c. Well, let's talk about what f of c means. Let's say x equals 3. So at x goes to 3 of the function, this guy's limit has to be equal to f of 3. What is f of 3? As a description. What are you looking for if I ask you f of 3 in a graph? The y value. So what we're saying is that the limit, because that's the definition that's up there, has to be equal to the y value for the function to be continuous. Okay? So, coming in from the left, coming in from the right, they have to go to the same place, and it has to be its y value. What it means is that point has to be right there. So what happens, though, if I do a removable discontinuity? The limit's the red circle, but the y value is the black point. Does that make sense? That's what makes it removable. Or sometimes you even have this. You don't even have a point. It just does that. So that's how you can tell that a removable discontinuity doesn't follow the definition of continuity. Endpoints. Everyone gets confused with these, but I'll show you a picture in a second. The left endpoint, so this guy's the left side. This is going to be the right endpoint. So a left endpoint would be coming like this. That's a left endpoint. Right endpoint would be going like that. Now that you see that, it should help you. The definition of continuity only comes from one side for your endpoints. Which side did I come in from? For the left endpoint, I came from the right side. So even though it's the left endpoint, oopsie, it wasn't supposed to be an L, f of c. Even though it's the left endpoint, you come in from the right. Even though it's the right endpoint, you come in from the left. And people get all kinds of confused with that. But you should be able to make sense of it with the picture. All right. So, in your own words, and to be honest, we're going to do my words so that it's a little bit quicker. In your own words, the definition. So, the limit as x approaches c must equal the y value. The limit has to be the same as the y value. That's my quick summary of the definition of continuity. Is this going to be on Monday's quiz? No, because we're in 2.3. I keep my section numbers. Please don't ask me that on Friday. Alright, so here's the picture so you understand real quickly what it looks like. This is the left endpoint. So you're coming in from this side. This is an interior point. That was the first definition I gave you. And the interior point, we come in from the left and from the right. And then the right endpoint, we only come in from the left. They gave you separate definitions because you can't use the real definition of continuity. You can't come in from both sides. Using the definition of continuity, explain in your own words why a removable discontinuity is not continuous. We just talked about it. What's wrong with it? The point might not exist, so there's one thing. The point may not have a y value. I want to use the word y value in it because that's in the definition. Or, what's the other thing that might have happened? Y value may be different. All right. Explain why using mathematical notation. This is really easy. It's because the limit as x goes to c of f of x will not equal f of c. It's a great thing about math definitions. You get to just put a not equals. All right? I do that so that it forces you to know your definitions, it forces you to know the words that we use, and it forces you to know the math notation. That's why I kind of make you rewrite it. All right? Types of discontinuities. Removable discontinuities, your easiest one. Yep, Matthew? Yeah? Tell you a weird, really cool fact. So some research has shown that if you don't go back and read your notes again for like 5 minutes, just go back and physically read it, you lose 70% of what you learned. That's why we do homework, but even in that homework time, you should look back through and just at least once read your notes all through the 7 classes that you take. 70%, that's a lot. That's a lot. Those smart research people. All right. Removable discontinuities. You can fill a hole. That's kind of what we talk about. So a removable discontinuity, the definition of it. So something like this. That's our little graph of it. The definition says that the limit as x goes to c of f of x does not equal... Oh, actually, let me start with this. Equals L, but f of c does not equal L. So the limit exists, so I'm going to say it in words. The limit exists, that's what this says with the L, okay? But the y value is not the same. That's literally the statement I just wrote in math, okay? Write it underneath if you don't know what that means. This literally just says the limit exists because I used a real L. And then this right here just says that the y value is not the same as that limit, okay? Write it in words. Then we're going to look at other discontinuities. So, categories, right? Removable. There's only one type of removable discontinuity. It is itself. But now there's 3 types of not removable. Okay? The first one being a jump discontinuity. So what does that look like? It looks like we go to a point and then we jump up higher and we go somewhere else. Right? So that's a jump discontinuity. So what's wrong with that? Well, a little bit more is wrong with that one. As you come in from the left of a jump discontinuity, is there a limit? Yes. I'm going to put a but. What's wrong when you come in from the right? Is there a limit? Yes, but what's wrong with it? It's different, so we use a different letter. That's how we say they both have limits. Jump discontinuities both have limits. They're just not the same limit. So what does that also say at C? The limit doesn't exist. Okay. Infinite. That's an infinite discontinuity once I use it. There we go. That's an infinite discontinuity. What are they the same as? Vertical asymptotes. So your vertical asymptote, we're going to do the full definition. The limit as x goes to c from the left of f of x will be either positive or negative infinity. What word goes in the middle of my definition? Or, big fat or, the limit coming from the right-hand side of f of x is equal to positive or negative infinity. Not both, but can be both. That's the math definition of or. It's weird. One or the other or both. That is the math definition of or. Oscillating is a little bit crazy. You can put a little box for this guy. This one is the only one that you don't have to know the definition for. So I'm going to write a definition, but I don't really like it because it's not specific enough. When you do the limit as x goes to c from the left, it won't exist. And the limit as x goes to c from the right won't exist. They just won't exist, and I'll show you why. And was I smart enough to have my calculator up again? No. So, let me show you what goes on with that guy. Whoa. Okay. Alright. Okay, so I can do this sine of, did I do an extra one? 1 divided by x, parentheses, zoom. I hope 7 is still trig. Alright. Alright, so you kind of see that it does this bouncy thing, and you're like, oh, it just bounces and it comes back. Alright, so we're going to zoom, and we're going to go in at 0, 0. So I'm going to zoom in. So now I'm closer. Now you see what's starting to happen, right? Alright, so there's 1, 2, 3, 4, and if we want to call that a peak, there's like 5 peaks maybe, right? Alright, so I'm going to zoom in again. So the 5 peaks just turned into, it just keeps getting worse. It's one of the oddest functions to look at to graph. That right there is an oscillating function. What it means is no matter how close I get, it just keeps getting worse. My way of describing it, I made a joke in my head. I won't say it because I'm recording. Alright, so let's talk about a parabola, okay? If you zoom into the part that's the most curved, or maybe I have an extra skinny, tiny skinny looking parabola, but if I zoom in right at that little vertex, what happens if I zoom in enough? It just ends up looking like a flat line. And that's what you would expect for the sine of 1 over x, is that every time I zoom in, at some point it should start to straighten out, and it doesn't. It just keeps getting worse. So that's this one guy. That is the one function that I personally know that oscillates. I don't know other ones. There probably are more because it has its own name. I feel like they didn't name this one, but that's the only one that I personally know. It doesn't show up on the AP test. I think it showed up once before, but the definitions, there are 3 of the non-removable, so I show them all. Okay, how many discontinuities have you learned total then? 4 total. All right, finding the exact location of a removable discontinuity. I want to know where the discontinuity is, then you're going to have to factor. In case you forgot how to factor this guy, which you will not be permitted to forget, there's the rule. And using the rule, A is x, and B is 1. So, x minus 1 times x squared plus x plus 1 all over x minus 1, x plus 1. So what happens to your x minus 1s? They're going to cancel. You have a removable discontinuity at x equal to 1. What did it simplify to? X squared plus x plus 1 all over x plus 1. So, what is the difference between graphing this, original, and graphing the simplified? What's the difference? The whole is gone. That's the only difference. Everything else looks the same. What I mean by that, pick a y value. Pick a crazy y value. Substitute it in, they will always be the same. 2.578. Substitute into both, they will be the same y value. Except for at x equal to 1. Here, it'll be undefined, but here, it will actually be defined. So, here's the part 2. Rewrite the function without the discontinuity. If I ask you to do the 2 ways, so there's one way, which is rewrite the simplified. And guess what? It's gone. There is no discontinuity anymore. There's method 2, which is the piecewise function, which is the one I usually ask you to do. If I ask you for the piecewise function, then you're going to give me the original function first, x cubed minus 1 over x squared minus 1, and you're going to tell me you're allowed to use that function for every single x value except for the removable discontinuity. And then you're going to give me the y value of the removable discontinuity, and you're going to tell me use that value. So this right here that I'm about to put in red, will be the y value. How do I get the y value? To where? Substitute back into the simplified form. 1 plus 1 plus 1 all over 1 plus 1. 3 halves. Piecewise function. Original. And this is the y value that you got from the simplified form. That red is the y value. Okay? That's how you create the piecewise form. We still got a few things left from day one. I think there's, see how many. This guy, I can actually fit this in. This is pretty easy. We're going to talk about this being the outside function and this being the inside function. The inside's really easy. What's on the inside? Squared would be what that says, x squared. So therefore, if you know that that's the inside function, replace it with an x. That's your outside function now. What is it? Sine of x. What did you just do? You created a composite function. What do I mean by that? You took your g function, and what did you put in place of the x? You put the h function. Meaning, I took this x, I blacked it out, and I put this in its place. That's what a composite function does. So, real quickly, if you know that this guy is continuous, and the easy way to tell is a domain of all real numbers, there's only one function I taught you guys that it doesn't work for. What function has a domain of all real numbers but isn't continuous? Definitely not int x, the greatest integer function. This guy has a domain of all real numbers, and he's continuous. What that means is the composite has a domain of all real numbers, and it is continuous. So as long as you know the parts are continuous, that's my easy way of saying it. If the part and the part are continuous, then the whole will be continuous. Makes sense, right? All right, same thing works for this guy. All right, get on out of here. All right, we got only a little bit more.